So we can apply inverse to the square root function. To do this, we first should find some reference points to work with. So I want to use the whole number coordinates. So I'm going to start with 3 and y equals 0. The next coordinate should be when square root 1. So 4 minus 3 is 1 square root. And then the next coordinate should be 7. 7 minus 3 square root gives me the whole number 2. And we're probably just going to use those points, but I'll use one more here. We're going to use 12, I guess. So 12 minus 3 square root gives me 3. Okay, so I'm going to use those first 4 reference points. So 3, 0, 4, 1, 7, 2. Okay, so these are going to be my reference coordinates I'm going to transform. So what am I doing here? I'm going to take all the x's and do an inverse. So x and y switch algebraically. X and y coordinates switch in the table. So my y coordinates are going to become 0, 1, 2, 3. Okay, switching those x and y coordinates then, I'm going to be able to generate my inverse function. So it's going to be 0, 3, 1 over 4 up, 2 over 7 up. Okay, so those are the coordinates I've transformed, and the graph's going to look like this. Now, if I do this on the graph here, I'll get a little bit better sense of the symmetry involved. Okay, so what I've done is I've taken the square root and I've reflected it across that line y equals x. We could also think of this as I've taken a square root function and I'm now dealing with the squared function or the parabola. So if you take a look at that, there's the parabola. Now I'm missing part of the parabola, okay, and there's some reason why I'm missing that. Well, obviously it's not an inverse. Okay, inverse means we switch x and y. There was no bottom half of this parabola to start with, so we're not going to get this part. And so this comes to the issue of when we start solving square root functions, square root equations. I want you to recall that when we solve square root equations, I had things like this: square root x equals negative 9. Let's say negative 3. Okay, and I solve this by squaring both sides. I use the inverse operation. So when I square it, I'm using the opposite operation. But the problem was the square and square root aren't actually perfect inverses of each other. So there's a bit of a problem anytime I use a square to undo a square root. Because notice what happens here. I get x equals 9. Well, that seems like a perfectly valid solution. But if I plug it back into my original equation, does square root of 9 equals negative 3? No, it doesn't. Okay, so this is a problem, is that when I square things, I'm going to end up with this parabola. And that parabola actually doesn't exist for the original square root equation. So this generates what we call, these are extraneous solutions that we found when we solved these equations before. So we can find extraneous solutions because the problem with squares and square roots is that they're not perfect inverses of each other. Therefore, when we undo square root with squares, there's this possibility that we're generating this parabola and we're actually working with this side of the parabola, which doesn't actually exist. Okay, so that is the reason why we have this issue of extraneous solutions with square roots. And we didn't have it with some other functions because the other functions were actually perfect. They were perfect inverses of each other. So that's one thing to note. Squares and square root aren't actually perfect inverses of each other, so we have to be a little bit careful when we solve them, undo one with the other. Okay, so here is another inverse. The inverse is, again, in basic terms, it's switching x and y. So I'm going to take all my x and y coordinates. So I'm going to use these reference points. Now, some people like to use a 0 here, but I think the vertices are probably good enough. So I'm going to start with negative 6, negative 3, negative 3, positive 3, 0, 3, 3, negative 3, and 6, positive 3. So those are my coordinates. I'm going to inverse them. Okay, which means I take all my x's and make them into y. So -6, -3, okay? And then I take all my y's and make them into x's. Okay, and I can graph this. So I end up with -3, -6, point down here, 3, -3, point down here, okay, 3, 0, point here, -3, 3, so that point there, so cuts through like that, okay, and 3 over 6 up, so that point right there. And that is the inverse graph of that other function here. Now, this, remember the physical property of inverse is a reflection across the diagonal line. So let's just test this. I'm going to make a copy of this. Okay. I'm just going to paste a copy here. And I'm going to take this copy and I'm going to put it on that graph. Okay, so there's that overlaid on top of that graph. Notice that is, yeah, that's my inverse, that's my mirror image across my line. There's my graph here. Okay, across this diagonal line, if I draw that diagonal line, you can see that the green image is a mirror image of the black image across that diagonal blue line. So that's what the inverse is. It's a switching of x and y, a switching of input and output, switching of domain and range, switching of x and y variables, a switching of x and y axes. It's going backwards through the function notation. That all those ideas are what we want to put to inverse. Okay. For us, for graphing, we just want to understand it as switching x and y coordinates. That's the simplest way to do it, and that gives us this mirror image.